Have you ever really stopped to think about the physics hiding inside a simple glass of water? Or what's happening in the air that lets a massive jet fly right through it? All around us are liquids and gases, what scientists just call fluids. And they follow this fascinating set of rules that, honestly, govern our world in ways we barely even notice. So let's pull back the curtain and dive into the invisible forces that shape, well, everything.
Let's kick things off with a question you've definitely experienced firsthand. You can push with the exact same amount of force on the sharp edge of a knife and the dull back of it, right? One glides through an apple like it's nothing, and the other just kind of sits there. So what's the deal? It feels super intuitive, but the physics behind it is actually the key to understanding everything else we're going to talk about. And here it is. The answer boils down to one simple word: pressure. See, pressure is just the amount of force you apply over a certain area. A sharp knife takes all that force from your hand and concentrates it onto a teeny tiny area, the edge. That creates a huge amount of pressure. But the back of the knife, it spreads that same force out, which means very low pressure. So the big takeaway here is, it's not just about how hard you push, it's about how focused that push is. Okay, so that idea of pressure is fundamental. You got to keep that in mind. But now, let's apply it to the main event here: fluids. I mean, what exactly makes something a fluid in the first place?
Well, it's pretty simple. A fluid is basically anything that can flow. It doesn't hold its own shape. And this is why the category includes both liquids, like the water in your glass, and gases, like the air we're breathing. The thing that really sets them apart from a solid is that they just don't put up a fight when you try to change their shape. They are literally built to move and flow.
So, if fluids are so happy to change their shape, what happens when we start putting pressure on them? This is where things get really powerful.
There's this incredible principle in fluid dynamics that honestly feels like a superpower. It's called Pascal's law. If you take a fluid that's enclosed in a container, think of a water bottle, and you press on one part of it, that pressure isn't just felt right where you're pushing. No, it gets transmitted perfectly and instantly to every single part of that fluid in all directions at once.
And this isn't just some neat science trick. This superpower is what allows us to multiply force in some pretty incredible ways. For instance, how could you possibly use this law to lift something as ridiculously heavy as a car using only the force you can create with your own foot?
And here's the secret: the hydraulic lift. It's ingenious. On the left side, you apply a small force on a small area, which creates pressure in the fluid. Now, thanks to Pascal's law, that exact same pressure travels through the fluid to the piston on the right. But here's the catch. Since the right piston has a much larger area, that same pressure creates a much bigger upward force. It's like a cheat code for force.
Let's put some numbers to that to see how crazy this is. Let's say the radius of the big piston is just 3 times bigger than the small one. Well, because area is based on the radius squared, its area is actually 9 times bigger. And what does that mean? The force gets multiplied by 9. A small push becomes a massive lift. You are literally multiplying your own strength just by using the physics of a fluid. And this is not some far-off concept. You use it every single day. When you press the brake pedal in your car, you are doing this exact thing. A small push with your foot creates pressure in the brake fluid, which then gets transmitted and multiplied to clamp the brake pads against the wheels with enormous force. It's Pascal's law that's stopping your car.
Okay, so we've seen what happens with pressure when a fluid is just sitting still. But what happens when fluids are on the move? Well, welcome to the awesome world of fluid dynamics.
You already know this next rule, even if you don't know its name. You know how when you put your thumb over the end of a garden hose, the water shoots out way faster? That's it. For a fluid like water, the same amount of it has to pass by every point in the pipe each second. So if you make the pipe narrower, the water has no choice but to speed up to get through.
This diagram here gives us a cool little map of the fluid's flow, using what we call streamlines. See how on the left, where the pipe is wide, the lines are all spread out? That means the fluid is moving pretty slowly. But as the pipe narrows on the right, look how the streamlines get all bunched up together. That crowding is a visual cue that the fluid has hit the accelerator.
And now, we're going to combine everything we've learned so far, pressure and fluid speed, to solve one of the greatest engineering mysteries of all time. How do airplanes actually fly? The answer lies in a brilliant discovery by a guy named Daniel Bernoulli.
I mean, stop and really think about that for a second. A fully loaded jumbo jet can weigh over 300 tons.
What kind of incredible, invisible force could possibly be strong enough to overcome all that weight and just lift it into the air?
This is it. This is the whole secret, right here. Bernoulli's principle is elegantly simple. As the speed of a fluid goes up, its internal pressure goes down. It's an inverse relationship. Faster flow means lower pressure. Slower flow means higher pressure. Remember that.
This is where the genius of an aircraft wing's design comes in. A wing, or an aerofoil as it's called, is shaped very specifically to mess with the air flowing around it. The top surface is curved, making a longer path, while the bottom is flatter. This shape basically forces the air going over the top to travel a longer distance in the same amount of time, which means it has to move faster than the air underneath.
And here's where the magic happens. According to Bernoulli, the faster-moving air on top of the wing creates a zone of lower pressure. Meanwhile, the slower-moving air underneath creates a zone of higher pressure. So what happens when you have high pressure pushing up from the bottom and low pressure on top? You get a net upward force. We call that force lift, and it's what holds a 300-ton airplane in the sky. Amazing.
Okay, so far we've kind of been talking about ideal fluids that flow perfectly. But in the real world, fluids have this property that's a lot like internal friction. So let's get real and talk about viscosity.
Viscosity is really just a fancy word for how much a fluid resists flowing. Just think of it as the fluid's thickness, or even its gooiness. A fluid with low viscosity, like water, flows really easily, but a fluid with high viscosity, like honey or molasses, flows very, very slowly. It's because the internal layers of the fluid are basically dragging against each other.
This table makes the concept so obvious. If we just set water's thickness to a baseline of 1, our blood is actually almost 3 times thicker. But then look at glycerine. Whoa, it's over 800 times more resistant to flow than water is. This one property is so important for everything from the oil in your car's engine to how blood flows through your veins.
All right, let's wrap up with one last, almost magical property of fluids that happens right where the liquid meets the air. Let's talk about surface tension. Think of the surface of a liquid like it's a thin, stretched-out elastic skin. The molecules on the surface are constantly being pulled inward by all the molecules below them, and this creates tension. This skin is always trying to pull the liquid into the shape with the smallest possible surface area, which is always a sphere. It's the reason why water beads up on a leaf and why raindrops are round. The liquid is just trying to hold itself together as tightly as it can.
So from the pressure that lets a knife cut, to the lift that holds up a plane, to the delicate skin on a single drop of water, the world of fluids is just running on these beautiful and powerful principles. So my question for you is this: now that you can see how these forces work, what other examples of this invisible physics are you going to notice in the world around you today?